newtons j hat. It is down, and I said up was positive. If you put down positive, then that would be a plus sign there. So that's the force on 3 from 1 plus the force on 3 from 2. So now we're going to have, that's going to be a small number there, and that's going to be close to that. So I'm going to guess somewhere around 20.3, no, it's bigger than that, 20.8 newtons j hat. And then I hat, I'm going to go with 5.6 newtons I hat. But someone's about to tell me what the real numbers are.
In the I hat direction, I have 2.7.
2.7? Okay. You had a strange look on your face, Anna, that you can't, the fact that you disagreed with what I had?
That was all. Yes, and I have 21.4 newtons j hat. Negative j hat.
Now, we haven't actually come up with the final answer yet, so let's not forget to do that. I put newtons in at this point, and I really didn't have to. I know my final answer is going to be in newtons, but I put them there anyway just to sort of bring us back to what we're actually trying to do. These are forces. So now I add like components. And so negative 1.52 newtons I hat. And minus 27.6 newtons j hat. Did I make Carol's error?
No, I didn't.
In my nice ideal world in my head, I'm imagining all of you looking at this and going, I can do that in my sleep. Apart from the Carol's errors. Since the question is what is the force, we have an answer. Done. If I said, what's the magnitude of the force, what would you do?
Absolute value.
Okay, but it's two-dimensional, so what would you do? Sticking absolute value signs around it is not sufficient for what's the magnitude.
Oh, okay, I guess put them together. Put them together?
How?
I mean, it's the total force, right? So.
Yeah, so how would you, I mean, putting them together, there are lots of ways of putting numbers together.
I guess add them together in my head, that works.
Okay, how would you add them together? Just do negative 1.52 minus 27.6?
No.
What would you do?
We have to do that again.
That again. Oh, what, law of cosines?
Just get a hypotenuse basically, and that'll be.
That is a way complicated way of doing it, but I guess you're not technically wrong. Depends on what you would use for that angle. Yeah, this is one of the reasons of going through this. Some of the stuff, when you're taking the first semester course, would have been no problem. But how do you add vectors? If I were going to add these vectors graphically, because I have two vectors, I have an I hat vector and a j hat vector, how would I add them graphically?
Do you mean like with a protractor and a piece of paper? Is that what you mean by graph?
Yeah, with a protractor and a piece of paper, what would you do?
I mean, you would draw the angle and, you create a system with centimeters to newtons or whatever and put like the end-to-end method, and then you would find the resultant vector.
Okay, you said end to end.
Head head to tail.
Head to tail, there we go. So I have, don't forget, I have this way. So I'm going, oops, to the left, 1.52 newtons. And then I go down 27.6 newtons. So now what?
Just like he said, the Pythagorean theorem would get you the
I
result.
didn't hear anyone say Pythagorean theorem.
Did he?
So
Oh, you did. Oh,
Not exactly.
yeah.
maybe I.
That's why I said this technically is not wrong, because this Pythagorean theorem is a specialized case for this, and that's why I said it depends on what angle you use. So Pythagorean theorem to find the resultant, the magnitude of the resultant. If we're putting it in a polar form, then we'd also find that angle right there. Well, first we find that angle and then add 180. Well, I'm hoping that was as much fun for you as I imagined it to be. Questions before we now get back to the 2 protons in the universe?
I hate to do this, but the other form, the where you have it in polar form,
How would you add it that way?
Yeah, I'm blanking on what you do with that. Could you just do a quick review?
All right, so you actually could draw this out and then draw the sum of the vectors, similar to what you had sketched out when you were talking about adding head to tail.
Right.
If you do it that way, just purely, I mean, it doesn't have to be the exact protractor and ruler, but I've got some force that's going down like this at a 235.77 degree angle, so that's that angle right there. And then from here, I'm going negative something down like that, until my final resultant is there. You know the lengths of these two sides. From the angles, you can figure out that angle right there, and then you can use law of cosines. Or what I traditionally do when I'm given this, and I suspect some of your calculators can you can just plug this in the right mode of your calculator and it'll do it. Or 7.5 cosine 235.77 degrees I hat plus 7.5 sine of 235.77 degrees j hat plus 21.6 cosine of negative 82.8 degrees plus 21.6 sine of negative 82.8 degrees. Oh, I hat and j hat.
Which is just what we did on the other side of the board, isn't it?
It is, the difference is that once you have it in polar form like this, if you just use the actual angle, assuming 0 degrees, 180,
right.
the negative signs will automatically come out of it. You don't have to think through, oh, I'm going to the left, so I need to put a minus sign in front of it. This will automatically put a minus sign in front of it.
Thank you.
Yep. And of course, much to your delight, I'm sure, there's a video where I go through this. Questions? And by the way, it did resolve one of my mysteries from last semester that I haven't quite figured out why Japanese hot brought up one of my videos. But if I make a video for physics 152, then the first letters should be PHY space 152. If it works for 152 or 252, I put PHY space X52. If it works for pretty much any of my courses, I either write all in front or PHY space XXX. So right off the bat. And then there's the lab that I have which works for all of them, which is the string vibrator lab. Except the word lab is not there. So I was about to go in and actually add the word lab to it, and then I thought, no. Anyone who's looking for that type of video on YouTube deserve to get a little physics class. But it finally resolved why I was getting strange connections to some of my videos based upon search terms. Any other questions? And just one more note on the bazaar. I forget what the exact search term was. I know XXX was one of them, and then there was some other word that was used. And they clicked on the video, and I'm thinking, you know, it happens. But the average duration of people watching that video who did that search, the porn-related search term, 27 seconds. On average, they went 27 seconds into the video before they thought, I'm not sure this is really what I want. All right. Back to my universe. I think we've established that they will go away from each other. So the big question is, how does one proton know the other proton exists? And I'm not going to accept mental telepathy or spidey sense or the all-seeing eye of Sauron.
Is it because both of them have mass?
Okay, but the other one still has to know the other one's there. Are you going with it's warping the space around them?
Yeah, like the curvature of time-space, since it's just those two, but...
If that were the major, I guess you could make the argument. I was gonna go with that's an attractive force, so that would explain if they were attracted to each other, potentially. But the repulsive force, it's not like they come towards each other and go, ooh, it's a proton, let me run away. Because there are negatively charged particles which are roughly the same mass, so I'm not quite sure it's sensitive enough to go, it's off from the proton mass by about 1%.
So that would require a force to be around the protons pushing on each other.
Hey, what?
Two forces pushing on each other. So like the electric field, I'm assuming.
Yeah, I was objecting or questioning your use of the word force when you just used it.
Yeah. I don't know another way to put it, or field or not.
Field is the correct term there. So basically, I think this was 1820s or so when they were trying to figure out this problem. And so they made something up. They said, well, the thinking was, before this shows up, there has to be something in this space already. This proton must be creating something. That when the second proton shows up, it has no idea the proton's there. What it does is it senses whatever is already in that space because of the first proton. And it reacts to that. Now, when they first came up with this idea of an electric field, again, they had no idea if this was right or not. As you can tell from the fact that it's still in the textbooks, it was right. It wasn't until about 60 or so years later that they finally came up with the physical evidence that electric fields actually do exist. So if the electric field depends upon only one object there, then it's giving off something. And I will sometimes use the term electric pheromones. Just please be aware, I'm probably the only one who will refer to it as such. If you're talking to another physicist or any student who's never had me before, and you make a reference to electric pheromones, they will look at you strangely. But it's giving off something which is affecting another object. Well, what we do know from Coulomb's law is that the force between the protons, so between, let's call this proton 1 and then proton 2. The force between the force on 2 from 1 is equal to this constant, Q1, Q2 over R squared, R1 hat. But if we're talking about something being given off by the first one that does not depend upon the second one, we need to get rid of that second charge, and so we just divide by it. So we lose Q2 over there, and on the right-hand side, we have this constant times the charge of the first proton, or the first object, over some distance squared, R1 hat. Since we're only dealing with one object, I really don't need subscripts anymore, and so I can just generalize it like we have some constant up front, Q, or big Q, whichever one you prefer, over R squared, R hat. Since we're no longer talking about a force, we're talking, to some extent, force per unit charge, which potentially is misleading, but this is the electric field. This is the electric field from charge 1, or generically, the electric field. It is an E with a vector symbol over it. And because in essence we have only 100 characters to play with, if you look at uppercase, lowercase, our alphabet, and Greek alphabet, we're repeating again. So to differentiate, if I am talking about the magnitude of the electric field, I could write it like this, or I could just write it like this. But because energy generally symbolized by an E without anything over it, this is what I will tend to do. I will tend to write magnitude of the electric field with the absolute value signs around the vector symbol, just to differentiate it from energy. So this E right here, not energy. And for those of you who have forgotten or not familiar with the notation, K is kinetic energy and U is potential energy. Let's look at the implications. Oh, I set the alarm for 5 minutes before the end of class. There's no clock anywhere. Time has no meaning in this room. So somebody remind me what R hat is.
It's a unit vector that points away from the center of whatever circle we're dealing with.
All right, so if Q is a positive number, what does that tell you about the electric field?
It's pointing away from the center of the circle. It's pointing away from the center of the circle.
Okay, and if Q is a negative charge?
Pointing towards.
Yep. So we can generalize it that based upon the formula, electric field lines point away from positive toward negative. Let's make it slightly more general. Or more inclusive, more, let's just make it more. If I have an electric field line that is going to the right, given this, what is one possibility for what's creating an electric field line going to the right?
A proton on the left and an electron on the right.
Okay, there's two. So I could have a proton on the right, or I could have or left, as you kids today are saying, or an electron on the right. Or both. So given this idea of electric fields, what's going on here is that I have an electric field line going right there when the second proton shows up, and it reacts to the electric field. Regardless of what's creating the electric field, it has no idea what's creating it. It just says, hey, there's an electric field line. Let's explore. If I put a proton in this electric field right here, which way is that proton going to go? Yeah, one person pointing in the right direction. Yep. All right. It's a groundswell, 3. So it'll move that way. If I put a proton in that electric field, which way is it going to go? It's going to be attracted, being repelled, being attracted. And here, well, both are happening. So we can now also make the claim is that positive charge put into an electric field is forced in the direction of the electric field. Or more informally, it's forced downstream. A negative charge, well, it's the opposite. If I put a negative charge in any of those arrows, they're all going to move to the left. So negative charge